Hey everyone, and welcome. Today we're going to break down something we see every single day, but maybe don't think about too much: light itself. It turns out there are two really simple rules that explain how it moves, and those two rules are the secret behind how we see, magnify, and even capture our entire world.
So, it all starts with a simple question you can literally go test right now in your kitchen. Have you ever actually noticed this weird thing with a spoon? The back shows you this tiny right-side-up version of yourself, but the inside, it flips you completely upside down. Well, the answer to this little kitchen puzzle comes down to the two secret actions of light: bouncing and bending.
Okay, let's dive right in. Before light can bounce or bend, it has to get from point A to point B. And its number one, non-negotiable rule: it always travels in a perfectly straight line. Now in physics, they have a fancy term for this: rectilinear propagation. But all it really means is light doesn't wiggle or curve on its own. And trust me, this simple fact is the foundation for everything we're about to talk about.
And the proof is, well, it's all around you. Just look at the sharp, clean edge of a shadow. That's your evidence right there. It's proof that light travels in straight lines, which we call rays. I mean, think about it. If light just kind of bent and curved on its own, all our shadows would be these fuzzy, blurry messes. This super simple ray model is all we need to unlock the secrets of mirrors and lenses.
So, when one of these straight-line light rays finally hits an object, it gets to a fork in the road. It has a choice to make. It can either bounce off the surface, which we call reflection, or it can pass right through it, changing direction along the way. And that's called refraction. Let's tackle the bouncing part first. All right, we are now entering the Hall of Mirrors. This is the world of reflection, of bouncing light, and it's where we're going to solve the first half of our spoon mystery. You see, that spoon is actually two different kinds of mirrors rolled into one. The inside, the part that curves inward, that's a concave mirror. Its job is to take light rays and converge them, or pull them all together. And the back of the spoon, the part that bulges outward, that's a convex mirror. It does the exact opposite. It diverges the light, spreading all the rays out. Now here's what's so amazing. All reflection, whether it's from a perfectly flat mirror, a funky curved spoon, or even a disco ball, it all follows two incredibly simple universal laws. Basically, light plays a perfect game of pool. The angle it hits the surface at is the exact same angle it bounces off at. It's really that elegant and predictable. And because of these predictable laws, curved mirrors have a superpower. They can collect a whole bunch of incoming light rays and force them all to meet up at one single super concentrated spot, the principal focus. This is the exact principle that lets you take a concave mirror, focus sunlight with it, and get a spot so hot it can actually burn paper. So, how do we figure out what we're going to see in a mirror? Well, we don't have to guess. We can actually map it out using something called ray tracing. By just following the predictable paths of a couple of key light rays coming from an object, the exact spot where those rays cross tells us exactly where our brain is going to see the image. It turns what seems like magic into simple, predictable geometry.
Now, this is where it gets really cool, because this table right here, this solves our spoon mystery. For a concave mirror, the inside of the spoon, the image you see changes like crazy depending on how close you are. Far away, the image is small and upside down. But look, see that last row? When you bring your face super close, closer than that focus point, bam! The image suddenly flips, it's right side up, and it gets bigger. This is exactly why a makeup mirror works.
Okay, so we've totally mastered bouncing light. But what happens when light doesn't bounce? What if it goes right through something transparent, like a window or a glass of water? Well, that brings us to our second world, the world of refraction. You have definitely seen this. You stick a pencil or a straw in a glass of water, and it looks like it's broken right where it hits the water. Your eyes are not playing tricks on you. What you are actually seeing is the light coming from the underwater part of the pencil bending as it travels from the water through the glass and back into the air to reach your eyes. That's refraction in action. And here's the key idea. Refraction happens for one reason and one reason only. Light changes speed. Imagine you're driving a car from smooth pavement onto some thick sand at an angle. The wheels that hit the sand first are going to slow way down, right? And that's going to cause the whole car to pivot and change direction. Light does the exact same thing when it goes from air into water or from air into glass.
And just like we have mirrors to control reflection, we've engineered lenses to control refraction. A convex lens, which is thicker in the middle, converges light, a lot like a concave mirror does.
And a concave lens, which is thinner in the middle, diverges light, just like a convex mirror. See the pattern here? It's the same two jobs, just a different way of getting it done.
Now for the part that I think is truly amazing. Bouncing and bending. They seem like completely different phenomena, right? But what's so incredible is that the mathematics that describes them is, well, it's almost identical. There's this beautiful, elegant unity hiding underneath it all.
And just like we did with mirrors, we can use a really simple set of rules to trace light's path through any lens. For instance, a ray of light that comes in parallel to the center line will always bend to pass through the focus point on the other side. And a ray that goes right smack through the optical center doesn't bend at all. With just two of those rules, we can predict exactly what an image will look like. And this slide just illustrates that unity perfectly. Just look at these two equations. One of them describes every mirror, and the other describes every lens. And the only difference, the only thing separating the entire world of bouncing from the entire world of bending is a single plus sign versus a minus sign. That's it. It's just so powerful.
So, last piece of the puzzle, how do we know if our image is going to be upright or upside down? Easy. We just check the sign on the magnification value. If you get a positive number, the image is upright or erect and virtual, meaning you can see it but you can't project on a wall. If you get a negative number, the image is inverted or upside down, and it's real, like the image from a movie projector. Simple as that.
Okay, so why does any of this matter? Because once you understand these rules, you can make light do basically whatever you want, and our ability to do that has completely changed the world. That light focusing power of concave mirrors, we use it in our car headlights to shape the light from a small bulb into a powerful parallel beam. We use it in those magnifying makeup mirrors we talked about. We even build giant ones for solar furnaces to concentrate the sun's energy and melt steel.
And what about the convex mirrors? The ones that spread light out? Well, their ability to give you a huge panoramic field of view is why they're perfect for the passenger side mirrors in cars, and for those big security mirrors you see in the corners of stores. They let you see a massive area in one small reflection. And honestly, our control over bending light with lenses is maybe even more profound. It's everywhere. From the eyeglasses that correct our vision to the cameras that capture our memories. And from the microscopes that reveal entire unseen worlds to the telescopes that let us stare into distant galaxies. It all comes back to being able to bend light precisely. So, the next time you pick up a spoon, remember what you're really seeing. You're witnessing the two fundamental rules of the universe in action. Every camera, every telescope, every pair of glasses, it all comes back to these two simple ideas. Light either bounces or it bends. And by mastering those rules, we've literally learned how to see everything.
But I have to leave you with one final, kind of mind-bending thought. We've built this entire thing on the idea that light acts like a simple, straight traveling ray. And that model works incredibly well. But it isn't the whole story. Because when you start to look at things on a really, really small scale, light stops behaving like a tiny particle and starts behaving like a wave. But you know what? That is a story for another explainer. Thanks so much for watching.